Hello, everyone. Our first session today of the technology track will be Scott Clark. Scott Clark is the CEO of SigOpt. His presentation title will be Exploring Trade-Offs in Experiment Management as Part of AI Platforms. As way of introduction, Scott Clark is passionate about empowering experts to achieve their full potential with optimization solutions. He conceived of the idea of SigOpt while completing his applied mathematics PhD at Cornell and proceeded to build and open source the metric optimization engine at Yelp to help solve this problem. This process taught him that optimization needed to be productized to be effective for enterprises, which led him to found SigOpt in 2014. Scott holds a PhD in applied mathematics and an MS in computer science from Cornell University and BS degrees in mathematics, physics, and computational physics from Oregon State University. He was first chosen as one of Forbes 30 Under 30 in 2016. Please welcome Scott Clark.
Hey everybody, thank you for joining us today. We've got a great talk for you that's going to lay out some of the lessons we've learned from working with industries and firms around the world, helping them augment the way that they do ML and AI. I'm going to start with a really brief introduction to what we do to help contextualize things, and then go into these three different lessons we've learned from working with some of the most advanced ML and AI teams in the world. So if you get nothing else out of this talk, hopefully you remember those three takeaways and you're able to apply them in your day-to-day jobs. So SigOpt was founded with the mission of helping accelerate and amplify the impact that modelers are able to achieve. And we do that by helping them with this experimentation and optimization part of the stack. And what this really comes down to is helping them tune their models as efficiently as possible to get the best results and spend more time on their domain expertise and where their context awareness can really help. As you heard in the introduction, I've been doing this for quite a while. I've been tuning models for more than 10 years, all the way back to grad school, where I found I kept running into the same problem over and over again, whether it was building a genome assembly algorithm at Lawrence Berkeley Labs or a computational fluid dynamics algorithm at Los Alamos. A lot of domain expertise went into building these systems. A lot of the cool, fun stuff was about how do we attack this problem, define the right metrics, etc. And then at the end of the day, it was up to the grad student, me, to configure that system in order to get it to its best possible results. A lot of times that meant just manual intuition. We used to call this grad student descent. Or it meant just brute forcing it. You get a 1 million CPU hour grant at a government supercomputing center, and you just close your eyes and hope for the best. Unfortunately, that doesn't scale as things get more complicated, and oftentimes in the real world, as Deepak was talking about, there's this massive opportunity cost to experimentation. So after grad school, I went to Yelp and worked on the advertising system. And I found the exact same thing. A lot of domain expertise was put into building an incredible system. A lot of context is needed to know what you're shooting for, how you define success, etc. But scattered throughout the system was a bunch of config files, a bunch of magic numbers, a bunch of constants that were said, oh, I tried this a couple of different ways, do not change, things like that. You look at git blame and it's 4 years old before there was a mobile site or whatever it may be. And all of this was opportunity that was being left on the table. The big difference between my work in grad school and at Yelp was if you could do this right, it wasn't just better papers you got at the end of the day, but a lot of money came out the other end if you could do it right in industry. So this led me to take my PhD thesis and open source it, as was mentioned, with the package Mo, or the metric optimization engine. And basically what I found there was a lot of firms have this problem. I went and gave tech talks at a lot of the companies that you guys work at today, about 25 different firms from LinkedIn, Facebook, Google, Microsoft, etc. And they all had a lot of domain experts building incredible tools, applying that context awareness, but at the end of the day, all of these systems had tunable parameters. And a lot of times they were being set via brute force, intuition, etc. It was leaving a lot of opportunity on the table, and it was frankly a waste of those experts' times. So 5 years ago, started SigOpt in order to help solve this problem. And we tend to focus on a specific type of model. One of the things we've learned over the last 5 years is that not every model is created equal. Not every problem requires the same depth of tooling or the same type of tooling. So there's a lot of different things where you might be able to attack a problem where you have clean tabular data and you're just looking to fit a line. And there's a lot of tools out there that can do that quite a bit better than Excel or whatever people were using previously. But then there's another type of problems, what Gartner calls differentiated models, that again require a different approach. They require domain expertise, context awareness. Think of recommendation systems, algorithmic trading strategies, advertising systems. This is why your companies hire experts like yourselves to help apply these extremely differentiated techniques and amplify the difference between you and your competitors. And these problems tend to be extremely valuable for the business. Line fitting is great, but having the best possible recommendation system can fundamentally change the bottom line of the business. So the way that SigOpt helps with this is bolting on top of these models, on top of these platforms, and allowing people to do that configuration, parameter, optimization as efficiently as possible. So you define what you can tune about the system, maybe different feature embedding parameters, different dimensionalities that you're, for like word2vec, different ways that you're transforming images or text or whatever it may be, different architectures of like a deep learning system, different traditional hyperparameters like learning rates, batch sizes, stochastic gradient descent parameters, etc. All of those magic numbers that either sit in those config files or you leave as defaults and just hope for the best. You tell SigOpt what you can tune, we give you a suggestion, a specific thing to try, you evaluate that within your system, and tell us with one or more metrics, with or without noise, how well it did. And we learn from that to decide the next thing to try and repeat. Underneath the hood is an ensemble of Bayesian and global optimization strategies. If you want to dive deeper into the math, we're at booth 2 downstairs, happy to talk about it, or we have 20 plus NeurIPS and ICML papers that we're happy to send you to go into that. But you can think about it at the high level as, how do I efficiently get to the best configurations of these systems, augmenting what I've already put into the problem. And we've been doing this, as I said, for about 5 years, and the rest of the talk is going to be about the lessons we've learned from integrating this with some of the leading firms in the world. So we work with everyone from algorithmic trading shops like 2 Sigma and several others with a combined assets under management over $300 billion. We work with firms like OpenAI and the world's largest streaming service, big technology firms that have over $500 billion of total market cap, all the way to the US intelligence community. Again, it's people who have a specific job they're trying to solve, and domain expertise is required for them to build differentiated models. We're about bolting on top of that system and augmenting it in order to get them to the best results as efficiently as possible. And for a firm like 2 Sigma, this can be extremely powerful. So they have $50 billion of assets under management. They have several hundred PhD quants that have been building models for over a decade. So a lot of expertise is in that building. A lot of different techniques have been tried. And by using SigOpt, they can focus on those techniques instead of trying to build this in-house, cobble together open source, or all of the other methods that they tried before leveraging our solution. So the 3 lessons, the 3 takeaways, if you get nothing else out of this talk, are as you're starting to build up these ML and AI platforms, make sure you balance flexibility with standardization, that you maximize your resource utilization, and that you do that in a way that helps you unlock new modeling capabilities. As Deepak was talking about in the keynote previous to this, this is incredibly important because the underlying tooling often changes, the approach often changes, and you need to make sure that you're leveraging the expertise that you have in-house as efficiently as possible. So first up, balancing flexibility with standardization. I'm sure a lot of you have already read through Sam's ebook on AI platforms. Obviously, there's a lot of different tools that need to be built in order to do this well. You need to think about things at the data layer, the modeling layer, experimentation, evaluation, the actual execution and productionalization of the model. There's a compute layer there. It's a big, hard problem that takes sometimes years to solve. But different investments in different areas can have a huge effect. And there's different things where, again, your specific problem can allow you to build very specific tools that differentiate you. As Deepak was talking about, they have a very specific set of tools, and a very specific set of problems that they need to solve better than everybody else. And that's really this layer. Data management, the actual execution of the models, how they evaluate them. These are things that your domain expertise requires a very specific solution. The high-frequency traders we work with look extremely different than that large streaming service tuning their recommendation system. That looks extremely different than an oil and gas company tuning their simulations. They have different needs, and those needs are very unique to the business. The next thing you need to be able to do, though, is as you're building up those AI platforms, is allow for flexibility. Your modelers want to use the best tool for the job. What was really popular 5, 10 years ago, using scikit-learn for everything, XGBoost is the state of the art, has shifted over time. Now people are using TensorFlow, they're using deep learning, etc. 5 years from now, that will be different again. And making sure that you can stay on top of that and build a flexible framework that allows you to modularly use the best tool for the job or use multiple tools really helps. So this is about using logistic regression where it makes sense, using deep learning where it makes sense, and then using something proprietary where it makes sense, and doing it in a way where you use the right compute infrastructure as well. GPUs aren't required for everything, but where they are needed, they make a big difference. This middle layer, and this is where SigOpt helps, is experimentation and optimization. So this is a unique layer in the sense that every single model has these tunable parameters. From the simplest random forest where you need to select the number of trees to the most complex CNN where there might be dozens of different hyperparameters, neural architecture parameters, and feature embedding parameters. All of them have this problem, but if you solve it in a way that allows you to modularly adapt to that, then you can use the same tool and standardize on it without creating any sort of constraints for your actual users. So again, domain expertise and differentiation helps here. This is an ML and AI platform. Your modelers need to be able to use the right tools for the job. That's flexibility. And then experimentation and optimization is standardization, where domain expertise doesn't necessarily help. And so SigOpt helps firms around the world regardless of what they're using. Again, it could be the simplest random forest or XGBoost model all the way to the most complex reinforcement learning or deep learning model on any compute environment. You need to maintain flexibility and not get trapped into lock-in of either the model or the actual compute environment. This allows teams to really learn fast and fail fast. Experimentation is about how do you get to the best result as quickly as possible, but also how do you throw away bad results as quickly as possible? How do you make sure that your untuned random forest, which may beat an untuned neural network, doesn't cause you to spend the next 2 years just looking at random forests when a little bit of tuning could have switched that ordering? How do you make sure that you're getting the most out of these models before they go into production? Deepak was talking about doing parameter sweeps as A/B tests in production. But if you can offline make sure that you get the best possible variance to A/B test, that can massively cut down on your opportunity cost that you lose from doing this. Another thing that this helps enable is these kind of higher level or secondary effects of connecting outputs to outcomes. Instead of just doing a grid search and trying to find the best log loss, now you can maybe look at multiple business metrics and look at competing trade-offs and say, what was the best possible thing that I could have done in this situation? And boosting the overall productivity of your users is a key as well. A large global technology consulting firm that deployed us globally said that 30% of their data scientists' time was spent tuning and tweaking, playing around, experimenting with the model. And that can be for everything from a predictive maintenance pipeline to a computer vision problem. You could know everything in the world about computer vision, but doing 10-dimensional optimization in your head is something that humans are fundamentally bad at. So again, flexibility definitely helps, making sure that you invest where you can differentiate and partner where it helps add flexibility. Maximizing resource utilization is this second thing that I want to talk about. If you think about kind of the trifecta of what you want to be able to do with your tools, it's about doing things better, faster, and cheaper. So resource utilization is about doing things faster and cheaper. How do you do more with less, or how do you unlock things that were previously impossible because they were perceived as intractable? So imagine I sat you down in the cockpit of this F-15, and I told you, tune all of these different knobs and levers, and then we're going to have you fly. And maybe for some of you, it's going to be night. Some of you, it's going to be in the snow. Some of you, it's going to be in high winds and things like that. It seems like an extremely difficult problem. But this is very similar to the problem you're faced with when you're downloading a new model, and you have all of these different hyperparameters and architecture parameters that you can tune and set. And oftentimes, it can be extremely time-consuming and expensive to evaluate how well that actually performs. In the same way that if I told you to set these and then you're going to go off and fly for a while and come back, it's very time-consuming and expensive. Brute force is not necessarily an option as things get more and more sophisticated. And ultimately, hyperparameter optimization is what you are faced with day in and day out every single time you look at this model. And people call it different things, from model tuning to architecture search to training and tuning to just playing around with the models. Oftentimes, this is an opaque process where a lot of code gets checked in and then nothing happens for 2 weeks as you're kind of doing things by hand, and then magic numbers come back and you move on to the next thing. And there's a lot of different ways that people attack this problem. There's a lot of great historical research here. For simple problems, brute forcing it was fine. The grid search, random search became popular about a decade ago. And then there's other global optimization algorithms, from simulated annealing to genetic algorithms to Bayesian optimization. And these all have different trade-offs. So again, we work with a lot of different firms that start with one specific type of way to attack this problem and evolve over time. And so one of the things we see most commonly is manual search. This is trying to solve this problem in your head. And there's a pro to this, is that it leverages any kind of intuition and domain expertise you have for that problem. So if you've been attacking the same problem for a decade with largely the same data set and largely the same model, you probably have a pretty good intuition of how it works. Unfortunately, as you take away any of those assumptions, as it becomes a different problem, a different model, a different data set, whatever it may be, that intuition largely does not apply. And again, you're doing high-dimensional optimization in your head, which at best is a waste of your time, and at worst leads you to terrible results. So again, and I'm guilty of doing this a lot with wasting government supercomputer hours, brute forcing it can be a great way to solve this problem. Just break it up into a grid and try everything. This is like trying to climb a mountain by just ahead of time laying down every single lat long and then just stepping there and measuring your altitude. Intuitively, it seems like an inefficient way to climb mountains, and in high dimensions, it becomes completely intractable. So there was this great paper by James Bergstra about a decade ago that talks about, okay, instead of doing that, let's do random search. Let's just try different things and see what works. And that can be a lot more efficient than that exponentially scaling grid search. But this is like trying to climb that mountain by jumping out of an airplane and just hoping you land at the peak, and then getting back in an airplane and doing the same thing over and over again. Luck is not a good optimization strategy, and it turns out it's not very efficient at finding global optima. So there's lots of great global optimization strategies that have been around for a few decades, simulated annealing, particle-based methods. Evolutionary search has become very popular recently. This is kind of akin to, on that mountain, drop a bunch of seeds, and then hope that eventually one day there's a tree at the top of the mountain. Again, extremely resource intensive, requires a lot of evaluations. One of the drawbacks here is you're doing a lot of expensive learning on the model itself. It's requiring a lot of evaluations, instead of something like Bayesian optimization, which is about building a map as you go. So as you start to climb that mountain, you're learning from what you did previously to decide what's the most intelligent place to go to next. And this can be a very efficient, derivative-free global optimization strategy that leverages less total evaluations of that underlying system. One of the main drawbacks of it, though, is that traditionally it's been very difficult to parallelize. But by having an ensemble-based method and having this hosted, it can have this server ask-tell-based interface that allows you to do this in a highly parallelized way, leveraging some of the benefits of something like random search, but having your cake and eating it too by having the best and most efficient solution as well. And for a firm like 2 Sigma, this meant fundamentally changing the way that they tune and deploy some of their models. Taking models that historically took 24 days on a open source, state-of-the-art Bayesian optimization system down to 3 days. So instead of it taking a month to deploy a model, now it was something that could be iterated on, something that could be learned from, and ultimately got better results, even though it took significantly less time. More information is available on their blog. The final thing that I'll leave you with is that attacking this problem away from something like manual search or a brute force search or something like that can also fundamentally change the way that you approach these problems. And this is about unlocking new capabilities. There's a big difference between going from trying to put a screw in with your hands and using a screwdriver. But if you get access to a power drill, not only can you do that more efficiently, but it allows you to attack completely different types of problems as well. And this can mean doing better modeling, not just doing what you're doing today better, faster and cheaper, but fundamentally shifting the paradigm as well. And this can mean attacking things like previously intractable models. If it takes a day to train your model, you might say, well, I don't do grid search or manual search, I just don't do any tuning at all. But if you can break that problem into smaller tasks, if you can parallelize it, there's lots of different ways to take something that would historically be intractable serially or intractable with these more naive methods and make it an attackable problem. And that can, again, get you benefits that would otherwise be left on the table. Another interesting thing that you can do is potentially optimize multiple things simultaneously. So 10-dimensional optimization in your head is hard to begin with. 10-dimensional multi-metric optimization in your head is just a whole order of magnitude more difficult. But by having a tool that allows you to make different trade-offs, accuracy versus inference time, trading strategies, Sharpe ratio versus a book size, false positives versus true positive, whatever it may be, you're able to basically say, I want to have the best trade-off and then have, as an expert, the ability to choose what I want to do next. And as these models get more and more sophisticated, again, there's a lot of things that often go untuned, a lot of things that are held static. You can artificially constrain yourself if you can only tune 2 things at a time or do a parameter sweep of 1 dimension at a time, et cetera. But as you start to attack these more sophisticated models, having the ability to handle hierarchical or conditional parameter spaces, constraints, things like that can really allow you to, again, augment what you're doing today, but get this additive boost from what you were previously restrained to. So those 3 lessons, again, the 3 takeaways are, when you're building AI and ML platforms, think about standardization and flexibility. And they don't necessarily need to be opposing goals. There are certain parts of your stack where you can standardize while maintaining flexibility, and there's certain areas where your domain expertise and the unique problem that you're solving really helps, and certain areas where you can augment your stack and get this gain that was otherwise left on the table. You need to make sure you're maximizing resource utilization. For some of our customers, thousands of GPUs get spun up when they're training a single model. Doing that via brute force does not scale at all. Also, it's very difficult to hire experts like yourselves. You need to make sure that you're not wasting any time on something that you can automate. Unlocking new modeling capabilities, again, allows you to completely rephrase this problem. Take it from screwing in a screw with your hand to a screwdriver to a power drill. You can fundamentally do different things, not just faster and cheaper, but better and different as well. So I'll leave you with that. If you have any questions or would like to dive deeper on any of this, we're downstairs in the expo hall at booth number 2, just as you come in the door. Happy to talk about the math. Happy to talk about some of the work that we've done with a lot of these different firms around the world. Happy to talk about whatever it is that you'd like to when it comes to experimentation and optimization. I'll also give a plug for Sam's book, which we help support on modeling platforms. This talks about a lot of these different trade-offs and where flexibility and standardization can really make a big difference. We're actually going to have a webinar coming up as well that's going to dive quite a bit deeper into modeling platforms more specifically, and that'll be coming up in about a month. Recommend you checking it out. And then I've given a couple of podcasts on the TWiML AI system. And the most recent one was a joint talk that I did with Matt Adareth at 2 Sigma, where he talks about a lot of this, but much more from his more unique vantage point as a modeling platform builder within this large hedge fund.